So welcome again. My name is Vincent. This is our first lecture in the unit linear algebra. So in this lecture, we are going to simply lay the ground by defining a few terms related to systems of linear equations, and then do a few examples. And then in the next lecture, we'll now be going into nitty-gritties of the topic systems of linear equations. So please feel free to subscribe to my channel so that you always get more updates on the lectures that will be posted, not just for linear algebra, but also other courses like numerical methods, engineering, mathematics, and applied mathematics, also calculus. So systems of linear equations and elementary operations. So we start by an appetizer. So let's start by an appetizer. So solve the following simultaneous equations. Probably this one has been done in your high school. So it's x1, 2x1 minus plus x2 equals to 1, and x1 minus x2 equals to 1. So here there are various ways you can solve this. You can either use elimination or substitution or graphical, whichever method you like, as you did them in your lower years. So solution of this one, if I decide to use what we call the substitution method, then from the second equation, x1 is given by 1 plus x2. And then when I replace this value in the first equation for x1, I'll have 2 x1 plus x2 plus x2 equals to 1. So this is 0, not 1. And then I equals to 0. This will give us 2 plus 2x2 plus x2 equals to 0. And so this would be 2 plus 3x2 equals to 0. And this means that 3x2 equals to -2. When you divide through by 3, you get x2 equals to -2/3. And then x1 will be 1 plus x2, which is -2/3, which will be 1/3. So therefore, the solution to this system, this set of equations, so therefore the solution is x1 equals to 1/3 and x2 equals to -2/3. So that's the solution to that given set of simultaneous equations. And then the second set of appetizer, the simultaneous equations are x1 plus x2 equals to 1 and 2x2 plus 2x1 plus 2x2, 2x1 plus 2x2 equals to 1. So here, solution. So if I can use the same method I used in the first case, substitution, then I say from equation 1, I have x1 equals to x2, 1 minus x2. So replacing this one, the second one, I have 2 into 1 minus x2 plus 2x2 equals to 1. And so I have 2 minus 2x2 plus 2x2 equals to 1. So then this will give me minus 2x2 plus 2x2 is 0. So then this is the same as 2 equals to 1. So this is an absurd situation whereby we are saying 2 equals to 1. Then so this really a contradiction. It's not possible for 2 to be the same as to be equals to 1. Or if you didn't use substitution, you can say or using elimination, say 2 times the first equation x1 plus x2 equals to 1, and then the other one is 2x1 plus 2x2 equals to 1. So I'll have 2x1 plus 2x2 equals to 2, and then 2x1 plus 2x2 equals to 1. So if I subtract, then I have 0 equals to 1. Cos 2x1 minus 2x1 is 0, 2x2 minus 2x2 is 0. So 0 equals to 1, which is still another contradiction. 0 cannot be the same as 1. So because of all this one, then we say this simultaneous equations do not have a solution. Do not have a solution. But even you could actually have concluded that one by seeing the structure x1 plus x2 equals to 1 and 2x1 plus 2x2 equals to 1. It's not possible. These two numbers equals to 1, and also when you multiply by 2, those numbers will get 1. That's not possible. So therefore, this set has no solution. And then if you consider another set, say number 3, C, solve the equation x1 minus 3x2 equals to 0. So for this one, I just given one equation. So solution, we see that x1 can be written as 3x2. And so if we let x2 to be t, where t is any real number, then x1 can be said to be 3t, because now I'm saying that x we put for t. So therefore, there are infinitely many real numbers. So any value of t you pick, you put into this equation, then you get the value of x1. And so there are infinitely many of them. And hence you say the equation x1 minus 3x2 equals to 0 has infinitely many solutions. And many solutions. So these three examples now takes us to what we characterize a different, take us to characterization of the nature of solutions of any given simultaneous equations or any given set of linear equations. But before we do that, let's define what we mean by a solution of a linear, a system of a linear equations, or just what a linear equation is. So definition of linear equation. So we say any equation of the form a1 x1 plus a2 x2 plus a3 x3 up to plus an xn equals to b, where a1, a2 up to an are real numbers, not all zeros, and b is any constant is said to be a linear equation in the unknowns, in the variables x1, x2, x3 up to xn. And the numbers a1, a2, a3 up to an are called coefficients. While b is the constant term. B is a constant term. And then note that the powers of each of these xi is 1. So that's what defines a linear equation. So this is the key thing here. Any equation of this form is called a linear equation. And then second definition, what we mean by a system of linear equations. So definition, system of linear equations. So system of linear equations now a collection of many of the linear equations. So this one is defined as a finite collection of linear equations in the variables x1, x1, x2, x3 up to xn is called a system of linear equations. It's called a system of linear equations. So now when we have many systems, many linear equations, we put them together, then that collection is what we call a system of linear equations. So e.g., for a set of m linear equations, in n variables, the system of linear equations is given as so now when we have now m linear equations and n variables, then this is how the system looks like. So I have a11 x1 plus a12 x2 plus a13 x3 up to plus a1n xn equals to b1. So that's the first linear equation. Second one, a21 x1 plus a22 x2 plus a23 x3 up to plus a2n xn equals to b2. So that's the second linear equation. Third is a31 x1 plus a32 x2 plus a33 x3 up to plus a3n xn equals to b3. And then you continue in this manner up to the m linear equations, which is of the form am1 x1 plus am2 x2 plus am3 x3 up to plus amn xn equals to b m. So this, let's call it 1, is what we call a system of m linear equations in n unknowns or n variables. So x1, x2 up to xn. And then we have m linear equations. And then now, after defining what we mean by a system of linear equations, then the next thing is now to define solution of a system of linear equation. So solution. So solution is a set of numbers so you say a solution is a set of numbers, is a set of numbers S1, S2, S3 up to Sn, such that substituting x1 equals to s1, x2 equals to s2, x3 equals to s3, all the way up to xn equals to sn for the unknowns. So remember, unknowns are x1, x2 up to xn. All the equations in one hold or are satisfied. The key term here is all. So you put those numbers S1 for x1, S2 for x2, S3 for x3, up to Sn for xn. Then when you replace into each of these equations in this system one, then each of them is satisfied, meaning that once you replace those values, then the left-hand side of each equation will be the same as the right-hand side for all of them, not just one of them or a few of them. All of them must hold or must be satisfied. So that is what defines a system of m linear equations in n unknowns. And this is how we define a solution of a system of linear equations. So just a few examples on examples of systems of linear equations. So starting with what already you did in high school, simultaneous equations. Those are examples. Just say A. We say x plus 2y equals to 3, and say minus 2x plus 3y equals to say 4. This is an example of a system of linear equations. So this will be a system of two linear equations in two unknowns x and y. And then, so here the value of m is 2, the value of n is 2. Two equations in two unknowns. And then another example, we can have x plus 3y plus z equals to 6. And then say 2x plus 4y plus 6z equals to 18. I say this is 3. And then 4x minus y plus 6z equals to 19. So here there are three unknowns and three equations. So m is 3, n is also 3. Three equations in three unknowns. And C, we can have x plus 2y plus z equals to 4, and say 6x minus y plus z equals to 10. So here, m, which means the number of equations, there are two equations, and n, which is the number of variables, is 3. So this is an example of a system of two equations in three unknowns. And then D, we can say x1 plus 2x2 plus 3x3 plus x4 equals to 9, and say x1 minus x2 plus 4x3 minus 7x4 equals to 17, and say x1 plus 3x2 equals to, say, 10. So for this case, m will be 3, because we have 1, 2, 3 equations, and then n variables are x1, x2, x3, and x4. So n is 4. etc. So you can give as many examples of systems of linear equations as you can. So that's how we define them. So in the next short video, we'll describe the nature of solutions of any given system of linear equations, and then do some examples on how to find solutions of simple systems of linear equations, and then give a general method or a general theorem on the possibilities of getting solutions. The three possibilities that you must always get to have either for solutions of any given system of linear equations. So thank you.